Good morning, students. Good morning to all. Today, the topic we are going to discuss is Ostwald dilution law. So, what does the Ostwald dilution law tells you about? It gives you the relationship between alpha, that is the degree of dissociation, Ka, that is ionization constant of acid, and C, the concentration of electrolyte. So, Ostwald dilution law gives a relationship between alpha, Ka, and the concentration C. So, it is given by the equation alpha is equal to Ka by square root of Ka by C. According to this, Ostwald dilution law states that the degree of dissociation is inversely proportional to the square root of concentration and directly proportional to the volume of the 1 mole of electrolyte. So now let us discuss the dilution law for a weak electrolyte. So weak electrolyte. For weak electrolyte, let us say acetic acid. So acetic acid is a weak electrolyte. So acetic acid undergoes partial dissociation to give acetate ion and the hydronium ion. So this is the dissociation of acetic acid. Based on this, let us write the Ka. What is Ka? Ionization constant of the weak acid, or we say equilibrium constant. So equilibrium constant or ionization constant is nothing but the concentration of the product by concentration of the reactant. So the concentration of the products include acetate ion concentration, the H plus ion concentration divided by the undissociated acetic acid. So water is in excess. So we are going to study at infinite dilution. So water we take it as a unit. So this is the equation for ionization constant of weak acid. Okay. Now let us write out at equilibrium. So what are the three species existing equilibrium are acetate ion, hydronium ion, and acetic acid. So the three species which are at equilibrium are acetic acid, acetate ion, and the H plus ion are hydronium. So initial number of moles, So initially we take acetic acid as 1 mole, and acetate ion is not formed, hydronium ion is not formed initially. After a time t, let us assume that the degree of dissociation, let the degree of dissociation be alpha. After time t, the number of acetic acid undergo dissociation, let it be alpha. So at that time, no acetic acid or hydronium ion undergo dissociation. So number of moles at equilibrium. The number of moles at equilibrium. So what is the remaining number of moles? Initially I take 1 mole, X is dissociated. So what is the remaining? 1 minus X. 1 minus alpha. 1 minus alpha is the number of moles remaining at equilibrium. So since alpha moles undergo dissociation, that will be converted to acetate ion, and also that will be equal to hydronium ion. Therefore, alpha moles of acetate ion formed and alpha moles of hydronium ion formed. So X is the number of moles when dissociated. That is the actual number of moles that get converted. So here alpha is undergoing dissociation, means the same amount of alpha is going to get formed as a product. So the product is acetate ion. How much? Alpha. The same is the hydronium ion also. So the final step is the number of equilibrium number of moles. The concentration at equilibrium. So what is the concentration at equilibrium? So you have to multiply the number of moles at equilibrium with the concentration. So 1 minus alpha into C, alpha multiplied by C, alpha multiplied by C. So when you multiply the number of moles with the concentration, it becomes the number of moles concentration at equilibrium. The number of moles that remains in equilibrium. Concentration number of moles at equilibrium we get by multiplying with the concentration. So with this we can now substitute the value in the ionization constant. So Ka, already we have Ka is equal to acetate ion concentration, hydronium ion concentration divided by acetic acid. So here we can substitute acetic acid. What is acetic acid? 1 minus alpha into C. Acetate ion alpha C into hydronium ion, that is again alpha C divided by acetic acid. Acetic acid is 1 minus alpha into C. 1 minus alpha into C. So you will get alpha square C square by 1 minus alpha into C. So you can cancel 1 C, left with alpha square C by 1 minus alpha. So this is nothing but Ka. So the Ka value is alpha square C by 1 minus alpha. So I can write here Ka is equal to alpha square C by 1 minus alpha. Let us assume here alpha is nothing but the degree of dissociation. It's very, very less. Acetic acid only partially ionized or feebly ionized. So the degree of dissociation is very, very low. Let us assume that this value, degree of dissociation, alpha value is negligible. Then we can omit this alpha. So we can write alpha square by C divided by 1. So 1 doesn't make change. So Ka is equal to alpha square C. So from here alpha square is equal to Ka by C, where alpha is equal to square root of Ka by C. So this is the Ostwald dilution law for the weak electrolyte. Okay. Similarly, Similarly, we can write the Ostwald dilution law for a weak base. Example for weak base, ammonium hydroxide. Acetic acid is a weak acid. Similarly, ammonium hydroxide is a weak base, weak electrolyte. So in that case, again alpha is equal to square root of Kb by C. So these are the two equations which we derived for the Ostwald dilution law for weak electrolyte. Okay, so let us conclude that the degree of dissociation is inversely proportional to the concentration of the electrolyte, whether it is an acid or a weak base, whether it is weak acid or weak base, degree of dissociation is inversely proportional to the square root of concentration. Thank you, students. Thank you. I hope you understand. Kindly subscribe, like, and okay. Thank you.